Welcome in, everyone. In this video, we are going to be introducing ourselves to functions, what makes a relation a function, ways to test if a relation is a function or not, and then talk a little bit about domain and range and then function notation. So functions, what makes a relation a function? A relation is any set of ordered pairs or sets of values, something that's been graphed on a coordinate plane. But what makes a relation into a function is that each input or x value has only one output or y value. So while we could have several y values for one input, anytime we see one x value, we have one associated y value with that. Okay, so we can't have two x values with different y values. We have to have 1-to-1 for every single x value. Okay, so we only have one y value for each x value. The ways to see that is, one way is to make sure that each x has one y. So if we see any x values that repeat, if they have different y's, then we know that relation is not a function. Because while all functions are relations, not all relations are functions. And then if we're on a graph, we can use what's called the vertical line test, where if we draw vertical lines all over the graph, none of those vertical lines would intersect our graphed relation more than once. We may have something that looks like this. And if I draw vertical lines through it, notice each vertical line I draw is only going to intersect it one time. So we know that that would be a function. If we have something that looks like this, and I were to draw a vertical line through it, well, that vertical line intersects that graph relation twice, so we know it is not a function. And when we talk about functions, specifically graph functions, we associate a lot of times with the domain and the range. The domain is going to be all possible inputs or x values, which would make the range all possible y values. And a lot of times these can be restricted based off of asymptotes or other factors we may have, like minimums and maximums. So when we look at domain and range, the first way we can write them would be as an inequality, where if we look at our graph and we notice our graph goes to the right up to 4 but does not include it, we would say x is everything that is less than 4. If it goes down along the y-axis to -2, and actually there is a point on our relation that has a y value of -2, we would say y is greater than or equal to -2. If we have a graph relation or a function and our x value starts at 1 along the x-axis and goes up to but does not include 8, we may write it like that, to where we have 1 is less than or equal to x is less than 8. That's saying that x is everything from and including 1 up to 8, but does not include that 8 because we have less than, not the or equal to. Likewise, let's say we have a y value where it goes down to -2, but doesn't quite reach -2. Maybe it's at -1.99999. We may have an asymptote, a horizontal asymptote there at -2, so it does not touch. Then we go up to -2, or up to +2, but again, it doesn't touch that +2. Maybe we have a horizontal asymptote at y equals 2, so it gets really close to that 2, but doesn't touch, we would have the less than sign. Now, if our graph goes forever and ever, we have arrows pointing to the right and to the left, as an inequality, we would have negative infinity less than x less than infinity. Now notice when we have these infinities, we use the less than sign, okay? Because we can never actually reach infinity. It just keeps going on and on towards infinity. We may also see this symbol, which just means all real numbers. So that would be inequality. Next we have interval notation, which interval notation is going to look a lot like a pair of coordinates. Okay, if we are looking at x less than 4, that's saying that the greatest value is 4, and we always put the greatest value on the right-hand side of the coordinate. And then because it's going on forever and ever to the left, going towards infinity, okay, I know we didn't write infinity, but since x is everything less than 4, it's going to go on towards negative infinity. We would have that. Now, with interval notation, we're either going to have brackets or parentheses. The parentheses are going to be our soft boundaries, where our values don't actually land on that value. So because it's less than 4, we're going to have a parentheses. And going towards infinity, with infinity or positive infinity, we'll always have a parentheses there. Okay? So with our interval, we would have our minimum and our maximum. And because we don't have a stated minimum, we would say it goes on towards infinity. With this one, because x goes from 1 and includes 1 to 8, we have our minimum, we have our maximum x value, and because 1 is actually a value in the domain, it's not a boundary, we would put a bracket. I like to think that's the concrete absolute that value exists in the domain, whereas 8 is not included, it's more just a reference point. We have the boundary, we have the parentheses for the soft boundary. And then if we were to do negative infinity to infinity in interval notation, we would just have negative infinity, infinity with parentheses. So you may see it like this, or this. All of those mean the same thing. Now, likewise, because we have y is greater than or equal to negative 2 being our reference point, and y is everything greater than it, negative 2 is actually going to be our low, our minimum, and it would go towards infinity. Remember, we put lowest to greatest here when we write this interval notation. And because we have the or equal to with negative 2, we're going to have a bracket there. With the infinity, we're going to have a parentheses. Okay, our interval notation for negative 2 less than y less than 2, we're going to have parentheses negative 2, 2, parentheses. Okay, and then again, for the all real numbers, we would have that as an interval notation. So let's practice identifying some relations to see if they're function, and then we're going to state their domain and range. Okay, so as I look at number 1, a lot of times for my vertical line test, I like to just use a pencil. Okay, and I use my pencil as my vertical line, and I'm going to go across the sheet and say, hey, my pencil, while it gets real close there, it's really just steep. My pencil never crosses that line more than once. So we would say it is indeed a function. And then I'm going to list the domain and the range, and I'm going to use interval notation here. So for our domain, I'm going to look to see how far left does my graph go along the x-axis. And I notice along my x-axis, the farthest left it goes is negative 6, because I have a point here at negative 6, negative 2. And now I look at my graph, I have a solid point there. That means that point does exist in this relation, which we've deemed a function. So I know I'm going to have a bracket with negative 6. And then I'm going to look to see how far right does my graph go. And I've got a point here at 7, 6. So I know 7 is going to be my greatest value with a bracket right there. So the farthest left it goes along the x-axis is negative 6. The farthest right it goes is positive 7. And again, I had a solid point there, so I put a bracket. Now, for my range, I'm going to look to see how low, what's the farthest it goes down along the y-axis. And while this may have been my minimum reference for my domain, my graph actually goes lower than negative 2. And I'm going to look right here. My graph goes to negative 7. Now, because it kind of goes down here and then jumps up, I don't see a solid point, but I do not see an open circle. I know that that is going to be -7 for our range. Okay, and then I see how far up it goes. It goes all the way up to +7. So there we go, +7. So again, sometimes I like to think, hey, if I put this in a box with vertical and horizontal lines, if I put my relation or function in a box, those horizontal and those vertical lines are going to help me see how far up, down, right, left, what my domain and range is going to be. Okay. Now, as we look at number 2, again, we would want to do our vertical line test. In fact, it does pass the vertical line test, so because no vertical line drawn here would intercept it more than once. So it is indeed a function. My domain, I notice my graph starts here at -6, +4, and keeps going to the right. So I have -6 for that x value, and I have an arrow here, so it tells me it keeps going on forever and ever towards infinity. So I'm going to have a parentheses. Now as we look at our range, remember, we go from lowest to greatest. While domain is lowest to greatest is going to be left to right. For our range, it's going to be bottom to top. So we look to see how far down is this going. Well, it's going at an angle. I agree it's going more right than it is down, but it is, in fact, it's going to keep going down all the way towards -infinity. And then I look at that value, how far up is it going, and it's stopping right there at 4 for our y value. Okay, so now looking at our next 2 examples, I look at 3. Again, I can use my pencil for my vertical line test, and I see, oh, that would intersect it 2 times. A lot of times the vertical line would intersect it 2 times. So we would say not a function. So then my domain, how far left does it go? It goes to -7, included. Okay, I don't see an open circle there, so I include the 7 all the way to 5 included. It's nice that it intersects the y-axis right there, or the x-axis, my apologies, the x-axis. Now here, our maximum doesn't quite intersect the y-axis at its maximum, but I see that it goes all the way up here to 4, all the way down to -4. So I'm going to have -4, 4. And that would be our domain and range for that relation, because it is not a function. Now number 4, is it going to pass the vertical line test? It is not, because it would a vertical line right there. It doesn't matter if it's all the time, as long as it's just one time, we know it does not pass the vertical line test, so it would be not a function. And then I look, it's kind of hard to see. Looks like I have an arrow going right here. We're going to say that's an arrow. So my domain, because it goes on and on to the left forever, because I have an arrow here and an arrow here, I'm going to have -infinity. And then as far right as it goes is this 6 along the x-axis, so I'm going to have 6 included. Now my range, it goes forever and ever down below, forever and ever up top. So there are 2 ways I can write this. I can either write -infinity to infinity, or I can just write all reals just like that. So that would be identifying a function versus not a function, as well as stating the domain and range of those functions or relations. All right, so the last part of this video is going to be what's called function notation. Function notation is simply where we have f or g of something. X is usually inside of here. This is telling us that this is a function based off of whatever x is. So our output depends on what our input is. And usually you see x inside the parentheses. More often than not, you see f of x, but sometimes you can see g of x, h of x, m of x, all types of things. But notice, this is not f times x. This is f of x, where the output or the function, the output of the function is based off of whatever our input x is. And a lot of times we may be given different functions in function notation. These just replace what we see as y, typically. And sometimes we may add 2 different functions together. We may subtract them, multiply them, or we may actually plug one function into another. where this is f of g of x, where whatever the g of x function is equal to, we plug that in for x into the f of x function and write a whole new function. And this can be either written as where it's g of x inside the parentheses, or we may see as f, and this is an open circle here. This is not saying f times g, this is f of g of x. Okay, so a couple examples we have, we're given an f of x function, 3x minus 1, and a g of x function is x squared plus 7, and we're going to go through the different examples we have. So we have f of 2. So when we have this f of 2, this is not saying f times 2, this is saying the f function where 2 is our input. So I'm going to plug in 2 for x, so that would be equal to 3, and wherever I see an x, I'm going to plug in a 2, and that would be 6 minus 1, or 5. Likewise, when we have g of x, so this is telling us we're using our g function, which is g of x up here. We have g of negative 5. I'm going to plug in negative 5 in for this x here. And when I do this, I like to put in parentheses to make sure that I am squaring the whole negative 5 together. So it would be 25 plus 7, or 32. Next, let's say I have f of x plus g of x. Well, I'm going to take that f of x function and add the g of x function to it. So that would be 3x minus 1 plus x squared plus 7. And then I'm going to use like terms. Well, I have that x squared, that 3x, and then plus 6 right there. So that would be our new f of x plus g of x is equal to that right there. Next, we have f of x minus g of x, and what I want you to pay attention to is because we're subtracting another function, I'm going to put parentheses around that function. So I have 3x minus 1 minus x squared plus 7. And the reason I put parentheses around there is so I'm subtracting all of the terms that are in that g of x. So I need to make sure I'm essentially distributing that minus, so it becomes 3x minus 1 minus x squared, minus 7, that should be a minus sign. Let me fix that, minus. So we'd have negative x squared, or the opposite of x squared, is equal to plus 3x minus 8. Okay, now let's get into our what's called composite function notation, where we're plugging one function into another. So we have f of g of x. So I'm taking that g of x function and I'm plugging it into the f of x function. So wherever I see an x in my f of x function, I'm going to take whatever g of x is and plug it in for that x. So that's going to become 3 times x squared plus 7 minus 1. And I would distribute that 3, so it would be 3x squared plus 21 minus 1. So our f of g of x is equal to 3x squared plus 20. Okay, and then likewise, if I have g of f of x, I'm taking that f of x function, 3x minus 1, and plugging in for x in my g of x function. So I'm going to plug in that 3x minus 1 squared plus 7. And I have to square this entire thing, so I'm multiplying 3x minus 1 times 3x minus 1, so you can think of it as that, because I'm multiplying this by itself, which would give me 9x squared minus 6x plus 1, because I'd have 3x times negative 1 and negative 1 times 3x to give me negative 3x minus 3x for minus 6x. And then negative 1 times negative 1 will give me that plus 1, and then we have plus 7 here. So g of f of x is equal to 9x squared minus 6x plus 8 would be our function. All right, so that is going to be it for this one. Hopefully I'll see you all the next one. Bye.